Welcome to another lecture on linear algebra. We are looking at the topic of spanning sets and linear independence. Let's go take a look at what we did last time and continue the conversation. So we have the topic of linear combination as a building block that is going to show up in all the exercises we do for this section. First topic we looked at was if we have given a set of vectors, how do we find out if a certain vector is a linear combination of those? Which means, can we multiply them by some numbers, add and subtract them to create that vector? Let's go take a quick look at what was done to answer this question. So for example, we had the first example. We had given two vectors. Let's call this u and v, and we want to make this vector t out of these two. So the question is, can I multiply this by number, this one by some other number, add them up to create this target? Well, we make an equation out of that, solve that equation by Gauss-Jordan elimination. In this particular example, when we came to the last stage, we saw that on the left hand side we have all zeros. On the right hand side in the last column we have a non-zero item, which means that this target vector cannot be built from these given vectors. So a set of zeros and the right hand side non-zero is a recipe for not existing. Then we had another example. Here's another vector t. We want to investigate if it is sum of these two vectors or linear combination of these two vectors, and we go ahead and solve a similar equation. Is it possible that this vector multiplies by a, the other one by b, and when they are added up we get our target vector? In this case, we went ahead and did the Gauss-Jordan, and it so happens that in this case left hand side is 0 and right hand side is also 0, so that the case of independent the lack of existence of a solution is removed, and we in fact in this case recover one value for a and b, which will do the job for us. So we said in these cases we go ahead and always verify that the answer that we have actually does the job. So in this case our result was that a is 3 and b is 2, meaning if I multiply this by 3 and that one by 2, I'll get that target vector. In this case it actually does happen. Occasionally there might be a parametric solution in this case, which means you have infinitely many solutions that your target vector can be built by many choices. Okay, and then we went one level higher up. That if some vectors are given to me like u, v, and w and so on, so that's a set of vectors, what are all the vectors that we can build by linear combinations? Okay, so what are the set of all possible target vectors that we can actually build them? And this is referred to as a span of S, span of that collection of vectors that we had, set of all linear combinations that can be built by the elements of S. Okay, to understand this topic, we went ahead, started some examples, which is if I have a vector u, just one single vector, what are all the linear combinations of it? Well, it would be all the multiples of u, which is going to be a line. Except for one extreme case, if my vector u was just a point at the origin, and all multiples of it will be still be the origin, and I collect them, I still get the origin. So at this extreme case, span of a single vector that's a zero vector is just the zero vector. Other than that, span of a single vector is going to be the entire line on which u is sitting. Then we pose the following question: if I have two vectors, what's the span of them? And we stop the lecture at that point and ask you to think about it yourself. So let's go ahead and answer this question. So let's go practice it. Suppose I want to look at all the linear combination of this, which means what? Like such as u plus v. So u plus v would have been So that one possible linear combination is that when I add them, I just come here. Well, what are other possible linear combinations? So for example, you can multiply this thing by 2 and then add it to v. Well, that brings you to this location. Or you can multiply v by 2 and add a u to it. That's going to bring you to this location. This topic might look familiar to you. We have gone through this issue before. What if I have 2u and 2v and I add them? Well, in this case, I arrive at this point. I don't have to always stick to positive numbers. I can do minus u plus v, and I'll be at this location. Or make both of them negative, and so on. So there's a whole set of possibilities, and if you put all of them together, what do you get? And that's the question you were supposed to answer last time when we stopped. Well, in general, you're going to get a plane. The span of u and v is going to be a plane in whatever space u and v are sitting in. So this is going to be a plane with, well, the given direction vectors with direction vectors u and v. Well, is it always like that? There are some extreme cases. Maybe you want to stop this thing and think about the extreme case. What do you mean the extreme case? Here, remember, we had the extreme case of when one of our vectors was 0. The span of that was just 0. Here, similar thing. If I have a set of two vectors and one of them happens to be a 0 vector, does that 0 vector actually help build anything? So if I have vector u as before, but if my v shrank to 0, well, no matter how many multiples of v I add to u, it does not change anything. So the span of u, if I put a 0 next to it, is not going to expand. It's going to be same as what it was before. So it's possible that you think that you have two vectors, but well, one of them is a 0 vector. It does not help in building anything, and the span just becomes a line. Well, is there something even more extreme than that? Well, yes. What if both of your vectors were 0? What would you be in that case? Well, you'll be back in that case of the span being the origin. So in any of these problems with respect to span of several vectors, there are extreme cases where one of them is 0. In case both of them are 0, well, you go back to the origin. So it can be the origin. If one of them is 0, the span will be line. Is that the only possibility where the span becomes a line? Well, no, there is still another case. If I have a vector u, and then my vector v to begin with is a multiple of u. If u and v coincide on top of each other, if I build anything out of u and v, that vector still gonna be on that same line where u and v were sitting on. So span of two vectors in a certain extreme situation can be just the origin. In several other cases where one of these vectors is actually multiple of the other one, the span becomes a line. Aside from these extreme cases, in general, in majority of the cases, span of two vectors is going to be a plane that contains u and v. And so on. The story continues. If I have three vectors and I want to talk about what's the span of three vectors, so if I have u and v and w, so we see that we're going from a point to a line to a plane, and next it's going to be a 3D hyperplane. So it's going to be, if you have three vectors in general, the span of them is going to be a 3D hyperplane, which sometimes we just refer to it as our ordinary 3D space, but in some extreme cases it could be the origin itself, it can be a line, it can be a plane, but the case that is the most common case is that it's going to be a 3D space and so on. Let's go ahead and investigate this issue in a little bit um, uh, more specific setting. So suppose I ask you find out what is the span of, and then I give you one vector, say 1 3, and another vector I give maybe 4 and 2. Okay, let's go and draw this thing. The question is, if I have one vector 1 and 3, and then another vector which is going to be 4 and 2, so this is the vector 1 3, this is the vector 4 2. Write it better. Vector 4 2. Well, we went through this exercise here. If I have two vectors and they are not multiples of each other, their span is going to be the entire plane. So the span is going to be the entire plane. And what do we call this plane? We call this plane R2. The span, when our vectors in 2 dimension, we are living in R2, and we are saying that entire space can be built as a linear combination of these two. Okay, so that's like talking in kind of very general terms. Let's make it specific. So okay, actually go ahead and build it for me. Meaning what? Meaning if I am at a location, let's call this location say A, B. Okay, you are claiming that a linear combination of these two is going to cover this entire space. In particular, it's going to cover this particular point. Well, tell me exactly how. What linear combination of these two is it that's going to produce that point for me? So that problem comes down to following. Find x and y such that if I take the x of the first vector 1 3 and the y of the second vector, so 4 2, is gonna bring me to the destination, the target point I want to be at. My target point is A and B. Okay, find x and y such that this happens. Now this is a little bit different from the equation you have seen before. We have looked at this situation once before. Like for example, find two numbers such that I get this as a output, but now my output is given in terms of two parameters A and B, and I want to find a combination based on A and B that brings me to that location. Well, since A and B are parameters and they can be any number, that point is going to cover the entire R2 space, and the recipe that I'm going to produce here is going to be good for all of them. Essentially, it's kind of like, let's say, killing all the birds with just one stone. Can you give me a recipe how to arrive at any point? Okay, so it's going to be a little bit different than other problems, but not really all that different. Let's go ahead and write this thing in a traditional equation. So when I multiply 1 and x, I get 1x, and this is 4y. 4 times y, that has to be a, and then this is 3x plus 2y, that has to be equal to b. So this is a system of equations just like any other equation we have solved before. It's just the right hand side of it is parametric. It's fine. We can go ahead and do it any number of ways we have learned. It's stuff we have learned in high school, or Gauss-Jordan method we have done here. Let's practice Gauss-Jordan in this parametric case. So it's a 1 4, right hand side is a. Let me separate right hand side from left hand side. And 3 2, and this is a b. What am I trying to find? Trying to find x and y. Find x and y. Well, x and y in terms of, so when we say find x and y, we are not insisting it has to be numbers. It has, in this case, it has to be in terms of the givens of the problem, which are those parameters a and b. Well, solving this thing is no different than any of the ones we have done before. For example, I go eliminate this one and eliminate that one, and then I'm all done. I have my x and y. So what's my first step? Minus 3r1 plus r2. Let me so go ahead and carry this thing out. 1, 4a. I'm not going to draw that line anymore. So I multiply by minus 3 and add them. So minus 3 times that plus this better be 0. Minus 3 times 4 is minus 12. And 2 is minus 10. Minus 3 times a, minus 3a, plus b becomes b minus 3a. Okay, what did we do next? We normalize this thing so that our pivot is 1, that less error prone, perhaps like that. So I take r2 and divide it by minus 10. When I do that, I get 1, 4a, 0. The idea is that to make this thing into a 1. When I divide by 10, this becomes b minus 3a over minus 10. In order there not to make mistake with the negative in the denominator, maybe we might be a bit cautious and do it write it like this. Multiply both of these things by minus, so I wouldn't make a mistake with my signs and so on. Okay, step B. Or step 2, get rid of 4. Oh, now it's easy. Since my pivot is 1, there's no mental pause here or something. So I have minus 4r2 plus r1. So what do I do now? I'll have 1 minus 4 times this and that. Well, that becomes 0. And then I have a minus 4 times 3a minus b over 10. And this was, well, 3a minus b over 10. The only trick in these problems is to carry out these additions and subtractions carefully so we don't make any sign mistake. So what is it here? I have a minus 4 times that, so it becomes 12a minus 4b over 10. Let me take a common denominator, so it's 10. It becomes 10a. Now here is the critical moment, minus. That minus is gonna change the sign inside. So minus 12a plus 4b, plus 4b here. So we get minus 2a plus 4b over 10. Okay, let's clean this up. So I have 1, 0, minus 2a plus 4b over 10, 0, 1, 3a minus b over 10. As soon as we have left hand side reduced to row reduced echelon form, we are done. In this case, if we have the cleanest solution we could have, I just have a string of ones here and I'm all done. So let's remember, if I had written x and y's all the way through, what would have been here? This would have been 1x and this would have been a 1y, and this is my right hand side. So this means what? This means, well, I've done with the problem. X is minus 2a plus 4b over 10, and y is equal to 3a minus b over 10. So for example, WebAssign might ask for a comma separated list, or create a vector for you and you fill it in and you do accordingly. Now let's make sure you understand what we did. What is the meaning of this? Show the meaning of this, or verify the solution. Okay, so you'll be asked to carry out this step on the exam and such to show that you understood what happens. What we mean here is the following. So we want to give an address for the location. Typically you say the address, well, take 3 blocks this way and 2 blocks the other way. Well, instead of 3 and 2 blocks, we have these many blocks and those many blocks. This is how many blocks to take in direction of the first movement, and the other number, this is the number of blocks to walk in the direction of the other one. Now we want to verify that if you actually do take these steps, you do arrive at that location. So that's what we mean by verification of the solution. So let's go ahead and do it. So I write the first one. So I have minus 2a plus 4b over 10. And I recommend not to simplify this thing, just leave it as it is. This was our x. The x was number of steps in taking the direction of vector 1, 3. And how about y? Y is 3a minus b over 10. And that's how many steps to take in the direction of our second vector. Our second vector was 4, 2. So okay, I take these many steps. Let's put in these many steps in direction of 4, 2. Well, if I take these steps, where am I going to be? Let's multiply this one with 1 and this with 4 and add them up. And this one by 3 and this one by 2 and add them up. So I'm going to make one big bracket here. 1 times minus 2 plus 4b over 10. And 4 of that, 4 of 3a minus b over 10. And then 3 of this one, 3 of minus 2 plus 4b over 10. And 2 of this one, 2 of 3a minus b over 10. Well, good that we didn't do anything to the denominators. Now I don't have to struggle to figure out a common denominator. All of them is 10. So 1 of that becomes minus 2a plus 4b. 4 of this becomes 12a minus 4b. How about down here? Same denominator. 3 of this is minus 6a plus 12b. 2 of this thing is 6a minus 2b. And you see the magic here, don't you? You see that? I got what? Well, 4b minus 4b cancel, 6a minus 6a cancel, and I have what? 12 minus 2a, so that's 10a over 10, and this is 10b over 10, and of course 10's cancel out, and what do we have? A and b. Isn't it what we were wishing for? We were wishing to arrive at a and b, and we were saying, okay, take this direction, take that direction, these many blocks of that direction, these many blocks of this direction. If you add them, it does bring you to the destination that you want. That is the location A and B that we wanted. So how does this problem show itself? So the problem shows it by the following. Show that R2 is the span of 1, 3, 4, 2. What we did is the answer to the following question. Now, this is sounding like some sort of a code or something, but just what it means is that any location in R2 can be arrived at by a linear combination of these two. We don't know what linear combination, so we took it as x and y. The destination, we called it A and B. We figured out what x and y is going to be in terms of A and B. So that was x. So this was x, this is y, and these were the two vectors, and that brought us to the location A and B. Okay, so that was this topic. So let me perhaps keep these topics separate from each other so they don't run into each other. And if you want to make a review of them, you come back to a particular video and you know exactly where it is. So we are going to make our videos a little bit shorter than before and try to have one topic at a time. Okay, so what is next? Let's go back to see what we have done. uh, we talked the span of two vectors in R3. We said it's a plane. So spanning sets, that's the problem we just did, 4 and 5. We are done with these two, and we want to find examples of linear dependence and independence. Before we leave, let me just do one more example of span of two vectors in R3. We already said if you have two vectors and then their span is going to be a plane. Now let's go and do some example in R3. That's the case we have done most examples in, and see how do we actually specify that plane. So here's going to be an example of the following. Find the general equation of the span of okay, so these are like two vectors. Let's call it maybe vector A and vector B. So I have vector A and vector B, and they're obviously not parallel to each other, or neither of them is 0. So the span is going to be a plane. So we know the span is going to be a plane, and it's sitting in three-dimensional space. So span is going to be some kind of plane. That's a plane. What we want is that the general equation of that plane. You remember the general equation was like ax plus by plus c z equal to d or something. And here we want the specifics of that. So if you have a point on this space, what are the coordinates of it? So x, y, z. I want to know what's the relationship with x and y and z. Once I find that relationship, that is the general equation of the plane. Well, how do we arrive at that point? We arrive at that by taking a multiple of a and multiple of b. So suppose this is a point R. How do I get to R? Well, when it comes to span, we are always starting at the origin, and then we have some multiple of say a and some multiple of b. So well, let's write this out. So x, y, z, that's the point we arrive at. It's a multiple of 1, 0, 3, and some other multiple of minus 1, 1, minus 3. What I want to do is to write this thing in as a general equation of a plane. General equation of a plane was ax plus by plus cz equal to d. Since we passed through the origin here, I know in advance that this one is going to be 0, so that is not an issue here. The question is, what's that little a, little b, and little c? Several ways of answering this. So you can do by cross product, you can do other things, but let's do in a method that is applicable to any dimensions and many similar problems. So I write this thing, so I'll have s times 1, so that's s, and then that is minus t, that's equal to x. Second equation is, well, t is equal to y. And third equation is 3s minus 3t is equal to z. What is it that we want to do? We want to eliminate s and t and just have x, y, z left, and that's what we call the general equation of the plane. Well, how do you so let's eliminate s and t. Let's do it two ways. One, suppose we are back in high school and we're doing this and we haven't done anything with respect to linear algebra. We don't know it's a Gauss-Jordan elimination and so on. What would you have done there? Let's just go back and do the problem that way. And then second time around, come back and do it by the Gauss-Jordan elimination, like a clean-cut way of doing this thing. So eliminate s and t, but I already know my t is y. So if I put it here, what would I get for my s? X is x plus t. Okay, my t is y. So that means that s is x plus y. So we are trying to get rid of our s's and t's. My s is x plus y. My t is y. So I go back to that third equation and say, well, I expect this thing to be true. 3 times s, which is x plus y, minus 3 times t, which is now y, that has to be z. Okay, look at this thing. There are no s's and t's in here. We eliminated s and t. Let's clean this up. This becomes 3x plus 3y minus 3y is equal to z. My equation simply becomes 3x is equal to z. That's what is left out of all of that when s and t were eliminated. Okay, so this is solution 1. This is a solution that in case you want to have some fallback style, this is something that's always available. Now let's go ahead and do it second style in Gauss-Jordan. So what is the matrix of this? On the left hand side I have 1s minus 1t. Right hand side is an x. My second equation is 0 and a 1, and here's a y. My third equation, 3 minus 3, and here is a z. Well, we do the elimination. So first thing I do here, minus 3 times row 1, I added to row 3, excuse me. So I'll have 1 minus 1 x. There's nothing here to eliminate. It's already echelon there. When I add 3 times this to this one, this becomes 0, and this one also becomes 0. Fine. And then this becomes minus 3x plus z. Now I reason like this. There is a reasoning that is subtle. Here I have string of zeros on the left hand side. If the right hand side is not 0, my system wouldn't have a solution and there wouldn't be an s and a t. For me to have a solution, whenever the left hand side is 0, the right hand side has to be 0 also, where this is 0, and that's what it tells me. Well, you can write it like this, you can write it like that, either way is fine. So this is the equation of the plane. Do you remember how to graph it and such? We had this a long time ago. 3x is equal to z. So this is my x, this is my y, this is my z. Z is equal to 3x. It's going to be a line here. And when you extend it in the y direction, that becomes, this is the plane that we are after. The span of these two vectors, is that plane. Okay, so practiced span. we talked about spanning sets. uh, when we say R2 is a span of that, there's another way of phrasing this thing. We say that this pair of vectors is a spanning set for R2, meaning you can build R2 on top of this. This is a scaffold out of which you can build R2. Okay, let me keep this thing short here, and then we're going to come back in the next lecture, and we are going to start on linear dependence and linear independence and all the other fun stuff. Until then, good luck and God bless.